Hi everyone. Um, so let me check all my levels. Sound looks okay. Looks like we have 10 people on the stream. All right. First of all, let me just say something about the test. Exact same format as before. It's 32 questions long instead of, I think the last one was 26, so it's a little bit longer. But I timed it. You shouldn't have problems doing it in roughly 1 hour, but you'll have the full 2 hours. Okay. And what does it cover? It covers the last two topics we did, which was conservation of momentum and rotational motion. Okay. So what I'm going to do today is I'm going to do some problems and like the ones that you'll see on the test. And well, that's it. Let's just start. Okay. So the very first problem is scroll back up here to the top. It's lots of parts here, and we're actually also going to do a variation on this. It's a simple problem, or it's a simple physical situation meant to try to help you with your intuition into conservation of momentum. Okay, so we have this 20 kilogram bomb, something that's going to explode into three pieces, and I give you two of the pieces and the direction that they're going to fly off in and the speed. So I have this M1, it's a 5 kilogram mass, and it's going to be traveling along the plus X axis at a speed of 15 meters per second. I mean, I call this thing a bomb, but like 15 meters per second is not that fast, okay? And we have a second piece, a 7 kilogram mass. It's going to be traveling along the minus X axis at 25 meters per second. And I sit here, note the sign, it's actually traveling along the negative X axis. I don't have any angles in this particular problem. I will in a variation of it. And we're going to answer some questions like what size is the remaining piece? What's the X component of the velocity of the remaining piece? What's the Y component of the velocity of the remaining piece? What's the magnitude of that velocity? What's the direction of that velocity? And I want the angle to be measured counterclockwise from the plus X axis the way we usually do. And then how much energy is released from the explosion. Okay, so I think, this should be sufficient to tell you what the situation is. But I've got a picture for you. We can take a look at it. Oh, I guess I don't have a picture. Hold on. Um, There we go. This program has been crashing, so I'm not going to be actually drawing. I have it pre-drawn. I don't know why sometimes it crashes and sometimes it doesn't. It's called Pinta, but anyhow, there it is. So what you're seeing here is, maybe I could just use my cursor here. You see that one piece is a 5 kilogram piece and it's traveling along the plus axis. The red dot is the is the bomb at the beginning. That's the full 20 kilogram chunk just sitting there at the origin, okay? And when it explodes, I mean, 5 kilograms goes off along the plus x direction, 7 kilograms goes in the minus y direction, okay? So you can see that it's actually going downwards there like that. And then there's a third piece which goes off in some direction, and I don't tell you. That's that third blue arrow. But here's where your intuition should help you. And this is really the point of the problem, is to help you with your intuition. You see that the 5 kilogram contributes to the x component of the momentum, okay, and not to the y. Why not? Because it's purely along the x direction. So the 5 kilogram has only an x component to the it only contributes an x component to the momentum. The 7 kilogram only contributes a y component, okay? So that 5 kilogram, it has an x component in the positive x direction. That means that that third piece, that's that third arrow right here, which I called M3 when we solve the problem, it's going to have a component, an x component to its velocity, v3x, which is along the minus y direction. Why the minus y direction? Because it has to compensate against the plus x direction, okay? And that 7 kilogram has a component along the minus y, so that third piece has to have a component along the plus y in order to compensate for it. Why? Because at the beginning, there is no momentum at all, and so after the explosion there should be no momentum at all. That doesn't mean, I should say, the total is no momentum. Doesn't mean that the 5 kilogram doesn't have some momentum and the 7 kilogram doesn't, and then that last piece will have some momentum. But when we add them all together, it better add up to 0, because if it's 0 before, if the total is 0 before, the total has to be 0 after. So this is the point of intuition. You should be able to recognize that that third piece had better be going off in the second quadrant, okay? So that when you solve this and you get that final velocity and you get that direction, you better find that that direction is in quadrant 2. Okay, so let's go back and solve the problem. Okay, let me just see here, check again my levels and everything. Yeah, everything looks good. I'm sure you guys would have told me by this point if you didn't hear me, if you couldn't hear me. Okay, so the first question is, what's the size of the remaining piece? That's actually not even conservation of momentum. That's just conservation of mass, okay? And I only put it in there. It's not trivial problem, but I just put it in there to show you that there are conservation laws all over the place. Energy and momentum are the two big ones in this course, but there's one that you probably know from high school days, and that's conservation of momentum, okay? And if we call that third piece M3, okay, well then M3 plus the 5 kilogram piece plus the 7 kilogram piece, that had better equal 20, okay? Because, just because the thing blows apart doesn't mean that there's going to be more mass after or less mass. If you collect all the pieces together and you weigh them after and you weigh them before, they better weigh the same. And so that means that the remaining piece is 8 kilograms. Okay, that was pretty trivial, all right? But there it is, conservation of matter. All right, the second question was, what is the x component of the velocity of the remaining piece? Okay, so the first thing you notice is, you have to identify the physics here, and the underlying physics is conservation of momentum. So you say to yourself, well, what's the momentum before? Well, the momentum before is this thing's not moving. In fact, I say that. Well, I guess I didn't say that. I probably should have said that. Originally at rest. Okay, don't worry, on the test I have my wording is very careful. Okay, so it's originally at rest. Okay, so this bomb is originally at rest at the origin. Well, that means that both the x and the y component of the momentum are 0, because remember, momentum is just mass times velocity. And so you could have all the mass you want, but if you have no velocity at all, if it's not moving, it's got no momentum. Okay, and that means that its x component is 0 and the y component of the momentum is 0. Okay, but here we're just worried about the x component. Okay, now after the explosion, that's that little prime there. That just means, after the explosion, we have that px is going to be the sum of the contribution to the x component from each of the masses. Okay, and basically, you just do mv, mv, mv. You just add up all the mv's, but it's just the x components. Okay, so you have m1 times v1, just the x component, okay? M2, V2, x component, and M3, V3, just the x component, okay? And what we're actually solving for is the x component of the velocity of the remaining piece. It's actually that right there, okay, V3x, because the third piece, I called it M3, and so V3 is its velocity and X is its X component, okay? And so now this is what you're going to use. Now, if you had more pieces, I mean, you would just write, MV for every one of them. For like if you had a fourth piece, a fifth piece, and so on. Like in a real explosion, you could have thousands of pieces, and if you added up the momentas of all those thousands of pieces, they would add up to zero, okay? I guess in principle it's hard to do because there'd be a lot of tiny little fragments, but here we only have three pieces, so this should be easy to do. So what do you substitute in for each of the numbers? Okay, so for px after, it's the same as px before. Why? Well, momentum is conserved. That's kind of the whole point of this. Okay, even though we have two symbols here, one px and px prime, that's just to say it's the same quantity, but viewed from two different temporal perspectives, before and after. Okay, but the number had better be the same. So if it's 0 before, well, then it's 0 after. That's 0. So there it is. Okay, and then m1 was 5. v1x, you say, well, what's v1x? Well, I told you that it's traveling at 50 meters per second along the plus x direction. Okay, and so if you go back to the diagram, let's do that very quickly here. Switch back there like that. Go back to the diagram. You see that the 5 kilogram has a component only along the x direction and nothing along the y direction. The 7 kilogram, on the other hand, has only a component along the y and no component along x. So v2x, that is the velocity, the x component of the velocity for the 7 kilogram, will actually be 0. So over here, all right, 5 kilogram, 15 meters per second purely along x, 7 kilogram, 0 meters per second along x. That doesn't mean that it's not moving. It's moving at 25 meters per second, but there's no component along the x direction at all. It's purely along the negative y direction, okay? So if it's purely along negative y, purely meaning there's no x component at all, that's why there's a 0 there, okay? So this is what makes it actually an easy problem. It's because they're both along an axis, you don't have to do the sines and cosines to break up the components. That's my next that's my variation on this. Okay, well, the third piece we found out was 8 kilograms, and we're solving for v3x, and so we get this, okay? And then, that this is just a matter of simplifying. So if add all this stuff up, it's 75, 8 times that, bring the 75 to the other side, negative 75 is equal to 8 v3x, divide both sides by 8, and you get that v3x is negative 9.375, okay, meters per second. All right, and notice that v3x is along the negative x direction, and you might say, is that what I expect? Well, let's take a look here, and we already argued this, but just to repeat now, the 5 kilogram is going along the plus x, and so you need something to compensate traveling along the negative x direction, and so that's why v3x has to be along the negative x direction. Okay, now it's always good to think, to go through this intuitively and say, yeah, I expect that to be negative, and it did come out negative. Otherwise, you might make a mistake in the sign. And you've seen this in the assignment. I mean, I'll have something like this, and I'll say along the negative x and along the positive x, and I expect you to know that it's traveling to the along the negative and not the positive, because the direction is critical in these problems of momentum. Okay, there's the first one. Any questions? No. Okay, let's continue. Part B is, what's the y component of the remaining piece? Y component of the velocity. Same thing. It's not moving initially, so both the x and y component are 0. Here we go. There's the y component. Okay. After, okay, it's 0 again, but now we can write it as the y component as the sum of all the three pieces. Okay. So that's m1, v1, but just the y component. m2, v2, just the y component, and m3, v3, just the y component. Okay. This time, the y component of the 5 kilogram mass is 0. Okay, and take a look at that diagram again. See the 5 kilogram, it's purely along x, no y component at all. That means that it's v1y. The y component of v1 is 0. Okay, so we're just looking up and down. Like, is that 5 kilogram moving up or down at all? No, it's moving purely to the right, and so it has no y component. All right, so that's why there's a 0 there. Okay. This time, the 7 kilogram does have a y component, but it's negative 25, because it's traveling 25 meters per second, but in the negative direction, the negative y direction, or along the negative x-axis. Sorry, the negative y-axis. Okay, so I emphasize that. I said note the sign, okay, because that the fact that it's traveling along negative y is important. Okay, if it were traveling along positive y, it'd be a different situation. Okay, so that's why we have a negative 25 there, plus 8 times v3 y component, and just simplify that and then divide by 8. It turns out to be positive 21.875 meters per second. Okay, so and again, just note v3y is along positive y-axis, okay, or the positive y-axis. And you go, why? Well, go back to the diagram one more time. 7 kilogram is going along negative y-axis, so something has to compensate for that, and that third piece will have to be traveling along the positive y-axis, okay, to compensate for that. All right, and by compensate I mean it has to cancel the 0 because it had no momentum before. So the momentum in the plus y and the momentum in the minus y, they have to equal 0 because they have to be the same as before. Okay, so that answers this question, okay, the y component. So now we have the x component and the y component. Now I ask for the magnitude. The rest of it is not really a part of conservation of momentum. It goes back to when we did 2D kinematics, but it's good to remind you how that's done, okay? So for the magnitude, it basically means, look, I don't want the x component and y components. I just want to know how fast it's traveling, irrespective of direction. Okay, so these guys are basically, projections along the axis. So if you made the keep going back to the diagram, but it's good to look at it. You see the that green dot there. If I were to extend a shadow along the y-axis, then that shadow or that projection along the y-axis would be traveling at v3y. And then if I also drop the perpendicular down to the x-axis, you get a little projection on the x-axis. It'd be traveling at v3x. Neither of them is its real velocity. They're just like projections of the velocity. But you can combine them to get how fast it's traveling along the blue line, which is its true velocity. And that's done using Pythagorean theorem. So v3, okay, is equal to the square root of v3x squared plus v3y squared. Okay, so basically square each of the components, add them together, take the square root, and you get the magnitude. Okay, so hopefully I'm not going too fast, but I don't want to waste your time with a lot of math that you should be able to do on your calculators. Okay, so that turns out to be 23.8 meters per second. So that's how fast that third piece is moving. Okay, one little check here is that the magnitude, whatever it turns out to be, has to be bigger than either the x or the y component. Okay, and so yeah, 23.8 is bigger than the 21, and it's bigger than the 9. Okay, so there you go. All right, there's the magnitude. And finally, what's the direction? And the direction here is given by, you know what? I'm going to get rid of that ugly theta there. Let me just cut and paste. I have my word processor up. Put in the proper symbol there. There we go. Theta, if you remember, measured counterclockwise from the plus x-axis, okay, is given by this formula right here. Okay, well, what goes into it? First, it's the inverse tangent, okay, of what? Of the y component divided by the x component. Okay, so it's the inverse tangent of the y component divided by the x component. But then you have to compensate if it's in quadrant 2 and 3. Okay, so if it's in quadrant 2 or 3, you have to add 180. You have to. You got no choice. You'll get the wrong answer if you don't. Okay, in quadrant 2 and 3. In quadrant 4, you can optionally add 360. If you don't, you're going to get a negative angle. And it's actually the right answer. But then you have to think of the negative as being measured clockwise. So if an angle is positive, you're measuring it counterclockwise, and if it's negative, it's measured clockwise from the plus x-axis. Okay, so I mean, I didn't want to overwhelm you when I first introduced this formula, but basically in the fourth quadrant, if you don't add in the 360, all you're saying is you get a negative answer, and all you're saying is measure clockwise rather than counterclockwise. clockwise. Okay, but anyhow, there's the angle. It's 313 degrees. And just to show you on the diagram where that angle is, if you start at the x-axis here, okay, right there, and you just start, turning counterclockwise, counterclockwise, counterclockwise. First, you'll get to the plus y-axis, that's 90 degrees, and then you go past that, and you get to there, and that turns out to be, that angle right in there turns out to be 113 degrees. Okay, is it 113? Yeah, 113 degrees. All right. Okay, so that gives you the direction. All right, and then the last thing, is how much energy is released in this explosion. Okay, and is the explosion elastic, super elastic, or inelastic? And well, let's do how much energy is released. Okay, so like when we did friction, we had energy that was macroscopic, and it appeared to disappear. It seemed that it disappeared. What it was really doing was being transformed into heat, but we don't understand heat yet. Okay, so it looks like this energy is disappearing. In an explosion, it looks like there's no energy there because the bomb is just sitting there, and then all of a sudden there is energy. And you go, where did that energy come from? It comes from chemical energy at the microscopic levels. Okay, so energy can go between macroscopic and microscopic, and when it does, it looks like, where did it go, or where did it come from? Okay, so that's why there's a possibility of it appearing that energy is created or energy is being destroyed. Okay, when it really isn't, if you take into consideration everything. Okay, so in this case, it looks like, because the bomb isn't moving beforehand, nothing is moving, that there's no energy there. Okay, it's like just this lump sitting there at the origin, and it's got no energy. Okay, and then once it blows apart into four pieces. There's the first piece, the second piece, and the third piece, and each piece just has a kinetic energy associated with it. Okay, 1/2 mv squared. Okay, and so the first one is 1/2 m1 v1 squared. Okay, and then m2, 1/2 m2 v2 squared, and 1/2 m3 v3 squared. Okay, and that allows you to calculate the total energy after. Okay, and so substituting in the numbers, we get this. Now, just a point here, that V1, that's just the magnitude. Don't, when it comes to energy, you don't have to worry about the direction. Okay, actually, that's what the square does. The square makes any signs or any directions go away. Okay, so you just do, how fast is M1 moving? How fast is the 5 kilogram moving? 15 meters per second. Great, just 15 meters per second squared. Okay, how fast is the second one moving? 25 meters. It doesn't matter that this one's along X and this one's along Y, so it's just 25 squared. And then the last one we found, was traveling at this 23.79929 and so on. And so you just put that in there and you work it out. And it turns out to be like 5,015 joules and some change, or 5.02 kilojoules, which isn't that much energy really. I mean, like, I don't know what the food energy is of a chocolate bar, but it would be in the hundreds of kilojoules range. Okay, so that's not really a lot of energy. All right, and finally, is it elastic, super elastic, or inelastic? Now, what does this mean? If it's elastic, the energy before and after would be the same. That means that this energy before, which is 0, and that energy after, which is 5 kilojoules, they would be the same. Well, they're not, and so it's not elastic. Okay, super elastic means that the energy after is bigger than the energy before. Well, the energy after is 5, the energy before is 0, and so the explosion is super elastic. Okay, inelastic would be the other way around. Okay, it would be where the energy after is less than before. All right, basically in an explosion, it's super elastic because you've got no energy or little energy before, and then you've got lots of energy after. Okay, things where collisions where things stick together, they're inelastic. Okay, because in sticking together, there's a lot of friction, and that's where the energy goes. Okay, so I don't want to make that a hard rule, but generally speaking, explosions are super elastic, and things sticking are inelastic. All right, let me take a look here if there's any questions about what I've done so far. I don't see any questions, so let me move on to number 2. Now, number 2 will go a little bit faster because it's really a repeat of all the same problems, but there's just one tiny change. The first one I made it the direction simple so that your intuition would kick in and you would see, yeah, the third piece has to be traveling off in quadrant 2. This second one, I actually made the 5 kilogram travel at 75 degrees to the plus x-axis. Okay, I still put the 7 kilogram along the negative y, but the 5 kilogram is at an angle at the 75-degree angle. Okay, so let me just show you a picture there, and let me switch. That's the old picture. There we go. Here's the new picture. So what do we have here? Well, we have, whoa, it crashed. I don't know why I got to switch my graphics program. It just seems to get into this situation where it decides to crash, and when it crashes, no matter how much I try to not let it crash, open, how annoying. Is it showing up? No, not yet. Properties. There we go. All right. Well, I'm going to be very careful here. We have the 7 kilograms still traveling along the negative y direction at 25 meters per second. The 5 kilogram is now no longer traveling directly along the plus x-axis. It's traveling at 75 degrees to the plus x-axis. Okay, and because it's like positive 75 degrees, you measure counterclockwise. Okay, so it's like that diagram, and it might be a little harder for you to intuitively see whether this thing is going to be in quadrant 2, or maybe you say it might be in quadrant 3, depending on how much momentum that M1 has. Okay, but it does turn out to be in quadrant 2. Okay, definitely it's either in quadrant 2 and 3, because it's kind of got to compensate. These guys are kind of traveling off this way, so it's got to kind of compensate to heading off that way. Okay, something like that. All right, so yeah, intuitively this one's a little harder to see, but definitely if you got an answer that was in quadrant 4, that would be wrong, right? Because if you see an explosion, you see a piece going this way, you see a piece going that way, and then you see a piece going that way, you naturally say, well, something has to be traveling in the opposite direction to make up for it. And if there isn't one, well, then that's not a physical situation. Okay, so let's do it. All right, and I just cut and paste these questions, but we don't have to do the size of the remaining piece. It's still 8. Okay, so what's the x component of the velocity of the remaining piece? Okay, well, it's slightly different now. These two are still the same. I mean, you still start off with no momentum, okay, in the x direction before, and you still have the same functional form for the x component of the momentum after the explosion. But what's changed is the value of v1x, okay? And the reason it's changed is because now well, let me switch back to the diagram. See that 5 kilogram, which is traveling at 15 meters per second. If I did the projection, I'd have a little bit of it being projected along the the plus x-axis, and I have a little bit of it along the plus y-axis. Okay, so it would have both an x and y component to it. And you say, how do I calculate that? Well, the same that as we've always done. It's basically the magnitude cosine the angle, okay, and cosine for x. All right, so that number is now different. Before it was 15 because it was purely along the x direction, but now it's at 75 degrees to the plus x direction, so it's 15 cosine 75. And if you put that in your calculator, you're going to get that number there. Okay, the y component for v2 is still 0 because, go back again, it's still traveling, the 7 kilogram is still traveling purely along negative y, and so there's no x component at all. Okay, so v2 x is still 0, and v3x, that's what we want to find. Okay, what is the x component of the velocity of the remaining piece? And the remaining piece, I didn't say it above, but the remaining piece is that I've been calling m3. Okay, so it's that 3 there means the third piece. Okay, so we have this. I just rewrote that from there. Okay, and we substitute in x component of the momentum after 0. Okay, 5 times the new x component of v1, which is that number right here that we just found. Okay, 7 times is 0 because there's no x component to v2, and then 8 times the third one. Okay, solving for that, I mean, that's a pretty easy equation to solve for. You just get this negative 2.42643 meters per second, okay? And the negative there, it's along the negative x direction, which is kind of what we expected, okay? Negative x, so negative x value here like that, negative x value, means that it's either going to be in quadrant 2 or 3, and that makes sense, okay? So now what's the y component? Well, these are again the same, well, functionally the same. So the y component of the momentum before is 0, and the y component of the momentum after is the combination of the contribution of the y component from each of the masses. This time, v1y right here, before it was 0, but now it's actually 15 sine 75 degrees, okay? And that turns out to be that number there, like roughly 14.5 meters per second, okay? So 14.48889 meters per second. All right. The y component of the 7 kilogram, that's negative 25. Okay, that's the same as before because its direction didn't change, and now we want to solve for that. Okay, so just substituting into that equation there. All right, the y component after is still 0. Okay, m15 v1y is this new value. Okay, I mean before in question 1 it was 0, but now it's this 14.4888889, okay, plus 7 times negative 25, okay, plus 8 times the unknown, okay, v3y, and then solving for that gives us 12.81944, okay, so the y component here is positive, all right, and so if we go back to the diagram here like that, you could see that you expect the resultant to be along the positive y. Sorry, I was about to sneeze. Okay, I didn't though. So the y component is along the positive y, the x component is along the negative x. Okay, and so you expect the resultant to be in quadrant 3. All right, and well, that's what we found. All right, so get the magnitude. v3x is just the square root of the x component squared plus the y component squared, and this time it turns out to be only 13 meters per second. Whoops, 13 meters per second. Okay, what was it before? It was faster before, I think. Before it was 23.8, and this time it actually turns out to be not traveling quite as fast. Okay, you do the angle, inverse tangent of the y over the x component plus 180. Again, 180 because we're in quad 2. All right, and this time that angle turns out to be, so here's the y component from like right here, right? And here's the x component. You just go up there. That's the x component. That's the, where are we here? That's the x component there. And you do the inverse tangent of the y component over the x component, and then add 180 for quadrant 3, and you get 100 degrees rather than 113 degrees. Okay, so yeah, it's different because the direction of the other two pieces are different. Okay, and just for good measure, and I hope I'm not going too fast here because this is just kind of a repeat. But if you work out how much energy is released, energy before is 0, energy after is same functional form, the only difference being that this number right here, v3, is a different number. Okay, v1 is still 15. I know that it's in a different direction now, but that doesn't matter. Okay, so remember that when you got that v squared in your energy formula, direction does not matter. Okay, so 15, and then for v2 it's still 25. v3, well, that's a different number now. Okay, that's this number right here, or I guess I put in that number there. And so this time I only got 3.43 kilojoules rather than the 5 kilojoules. Okay, and I didn't say it here, but this is going to still be inelastic. No, super elastic. Okay, why? Because the energy after is greater than the energy before. Energy is released. That's called superelastic. Okay, so I'll pause for a second, take a look if there's any questions. All right, I'm not seeing any questions in the chat, guys. Don't be afraid to tell me if I go too fast. there's always this competition in my mind between not wanting to waste your time and at the same time, not going so fast that you can't keep up with me. Okay. So I only did that second question to show you that, in general, expect these things not to necessarily be along the plus or y axes. They could be at some angle like you saw in this one. Okay. All right. I'm not going to do a problem. I'm not going to do a problem on 1D conservation of momentum. Those are really easy. In a sense, if you could do this, you can do those. And I'm not going to do a problem on where is the center of mass. Those are also pretty easy, okay? And we did do them before, okay? And they were also in your assignment. So I refer you back to that, okay? If you do want me to do one, of course, I can always do that, and you can make the request. But I'd rather go on to the rotational motion because that's going to be more involved, okay? So let's take a look here. Whoops, you can't see that full question. Yeah, you can. Okay. All right. So here's another question, or a different question. We have a rod, and it's a length of 120 centimeters. Okay. I could just as easily have said, instead of 120 centimeters, 1.2 meters. Okay. Like that. It's the same thing. So a rod of length 1.2 meters and mass 3 kilograms. Okay. And it is free to rotate around its center. All right. So I hope you can picture that. I don't have a picture, but just a rod, and this rod is allowed to, like this is a rod, and it's free to rotate around the center. Okay. The other possibility with a rod, if you go back to the recorded lectures, is rotating around one of the endpoints. Okay, like that. Okay. That's not my situation here. I said free to rotate around its center. Okay, so it's rotating like that around the center. All right. And it's initially at rest, and we're going to apply a 100 Newton force at 20 centimeters from the center at an angle of 45 degrees. When we get to this one, maybe I'll draw that picture because I think that one's a little harder to see. But this one I don't think you need a picture. All right. So now, what kinds of questions could I ask about this? Well, if you could sort of picture where I'm going to go with the problem, it really helps. I used to. I'll never forget when I was like a student. I could sort of anticipate what kinds of questions the professor would ask. Okay, even in the upper level years where they became more sophisticated. And so I would practice that. I would practice those kinds of problems, and I would do pretty good on exams because they were usually my guesses were pretty good. And that's because professors are always like, they don't want to throw something at you that's so fantastically different that you're like, what is this? Did we even study this? I mean, I've had exams like that myself where I look at the exam and I go, did we even study this in class? And those are not fun exams, okay? So you could, kind of see where I'm going to go with this. You say, well, where are you going to go? Well, I'm going to ask you to calculate the moment of inertia, and then I'm going to say, look, you're applying a force to something that can rotate. The force is a torque, or it gives rise to a torque. And that torque is going to give rise to an angular acceleration. So I'm probably going to be asking you stuff to do with tau is equal to I alpha. That's the Newton's second law, but in angular form. So, F equals ma is the linear form, tau equals I alpha is the angular form. Okay, so you can kind of see that this is a tau is equal to I alpha type problem. Okay, so let's do it. All right, so the first question I ask is, what's the moment of inertia? Now, when you go to calculate moments of inertia, there's a few possibilities. One, I could tell you, look, there's just these masses, point masses, and they're at certain points in space, and then you just do mr squared. You just add up mr squared for each one of them. But sometimes you might say, look, you have a rod, or you have a ball, or you have like a disc or a drum. A drum is really just a fat disc, okay? Like if you take a drum and you squish it down so it's very thin, a drum becomes a disc. Okay, so the formula is actually the same for a drum and a disc for the moment of inertia. Okay, and so you just have to identify which one of those moment of inertia formulas do I want to use. And for the rod, it's actually interesting because I gave you a formula for when the rod is rotating around the center and another one for when it's rotating around the end point. Okay, and so here, when I tell you that the rod is rotating around the center, and so the formula is this one. 1/12 ml squared. Okay, and I didn't prove why that's the value that it is or why that's the formula, but it is. And there's actually a Wikipedia page that has all of these formulas for all different shapes. Okay, and I'm not going to throw anything at you that isn't a shape that we studied. All right. But just so you know, there are a lot more shapes. I guess I mentioned this a lot for PTs because often the human body, when you start to do kinematics of the human body, or ESS, sorry, when you start to do kinematics of the human body, sections of the human body are often modeled as rods and discs and so on. Okay, and so you can get a handle on what the moment of inertia is of whatever part of the human body that's moving. Okay. Anyhow, I digress. So the moment of inertia for a rod rotating around the center is 1/2 ml squared. Sorry, not 1/2, 1/12 ml squared. So the mass is 3. I said it's 3 kilograms. The length of it is 1.2 meters squared, and so that turns out to be 0.36 kilogram meters squared. Okay, and those are the units for moment of inertia. All right, so that was easy enough. Okay, so just again identify the formula for the particular shape of the mass, and then plug in. Okay, great. Now what's a torque due to the force? Okay, so actually let me get rid of that and let me put the proper symbol in there. I have to cut and paste it from another program from my word processor, but it's basically tau is equal to, and let me get rid of that theta as well, and just put in a proper symbol there like that. All right, there we go. Okay, so it's tau is equal to RF sine theta. Okay, and how does that all work? Well, let me switch to my other whiteboard here, and let me start off with a fresh page like this. And so hopefully this won't crash. Okay, and there it goes. All right, hold on. Yeah, that program sucks. Okay. Unfortunately, I don't have anything else that I can use right now. There we go. It won't. It shouldn't crash this time. Let's see what happens here. All right. So here's the rod like this, and there's the center. Well, I guess that's kind of off, but all right, close enough. There's the center, and then what do I say? I say that we apply a 100 Newton force, 20 centimeters. Okay, so like the whole thing is 120 centimeters long. So that whole distance there is 120 centimeters. Okay, or 1.2 meters. Okay, so it's pretty long. So half of this, if you just did like that piece there, that would be half of 120, it'd be 60. Where we're not even anywhere near that. We're at what did I say? 20 centimeters. So somewhere, let me do it in blue, somewhere like 20 centimeters, like maybe right about there, is where I'm going to apply the force. Okay. Now to get this thing spinning, you'd like to apply the force actually perpendicular. That would be when you're like going to really start to get this thing spinning. But I don't even do that. I actually apply it at an angle. And what's the angle? At 45 degrees. So I apply this at an angle of 45 degrees like this. And by the way, it doesn't matter whether it's 45 degrees this way, because my problem's slightly ambiguous, but the ambiguity doesn't matter. 45 degrees that way, or if I apply it 45 degrees this way, where that's 45 degrees like that, it's still the same torque. Okay, so like that. Okay, so we're actually applying a keep forgetting my numbers here. 100 newtons. Okay, so this is a 100 Newton force like that, being applied at 45 degrees, and that distance right in there, that I'm drawing in blue, that's only 20 centimeters. Okay, so I think you could see that that would get this thing turning. It's not as good as if I actually applied the force perpendicular like that. Okay, like when you go to turn a door, first of all, you don't want to, like if that were the hinge, this black dot right here, well, I guess I'm making it red now. If that red dot there is the hinge, to turn the door, you'd like to press right over here. That would be the best place to press, as far from the door as possible. That's why the hinges of the door are on one side and the doorknob is on the other side, okay? And the second thing is you'd like to push perpendicular. That's when you'll get the most torque. If you push at an angle, like, that 45 degrees, you're going to get less of a torque. Okay, so anyhow, there's the picture, and let's switch back here, and there's the formula. So, just because you apply force doesn't mean you're actually going to get something turning. It's got to be pushed at some distance from the axis and at some angle. Okay, so that first R, that first parameter there, R, is how far is it from the force to where the thing is rotating, its axis. Okay, and I told you that it's 20 centimeters. Okay, so over here we're going to put 0.2 meters. All right, and then the force, how big is the force? Well, I told you it's 100 newtons. So there we go, it's 100 newtons. And it's sine, and what's the angle? 45 degrees. Okay, like that. And that's the angle that the force makes with the radial vector, or let me go back to here. Um, So that 45 degrees, if I were to say extend this, actually let me draw it in a different color. Let me use red here. Suppose I were to extend this like this. Okay, so that's like the radial vector means like starting from the middle here and then going out. Okay, that angle in there to the force is 45 degrees. Okay, so that's how you measure that angle. All right, so it's 45 degrees, and if you just work this out in your calculator, which I'll do in 1 second. You get, oh, it says it's a malformed expression. How come? Yeah, it doesn't like my expression. Okay, let me try again. Oh, it still doesn't like it. What? There we go. It's going to equal that number there. Okay, so 14.14, and the units are, that's why I put the units here, newtons and meters. Okay, so a newton meter, like that. Okay, by the way, just an aside, a newton meter is also a joule, but when it comes to torques, we always just leave it as a newton meter. Okay, it kind of makes more sense because you see the newton here is the force, and the meter here is the R. Okay, so we don't convert that to joules. It looks funny. It wouldn't be wrong, but I mean, no one does that. Okay, all right. So good so far. Let me see if there's any questions. Nope. All right. So now what? Well, now I ask for what's the angular acceleration, and you go, is there a relationship between the torque, the moment of inertia, and angular acceleration? And the answer is, of course, yes. It's tau is equal to I times alpha. All right, let me grab an alpha here. And paste. There we go. Okay, tau is equal to I alpha. That's the angular equivalent of F. So tau is like F, is equal to m, so I here is like m, times a, and a is like alpha. Okay, so one is just the angular equivalent of the other. And of course now we have I, and we have tau, and so we can find alpha as alpha is equal to tau divided by I, which is equal to this number divided by this number. And what does that work out to? It works out to this number, 39.28. And on a test, of course, I would round that off to 39.3. And what are the units? The units are radians per second squared. Okay. At this point, you might go, whoa, where did the radians come from? Because over here there are no radians, and over here there are no radians. And just remember that radians are not a real unit. You could have written 1 divided by second squared, but we do write radians in there just to kind of remind us that we're talking about an angle here. Okay, and one turn or one revolution, just to remind you, one revolution is 2, where's my pi? 2 pi, There you go, 2 pi radians. Okay. And you might say, well, why do we work in radians and not in degrees? Okay, because obviously 1 revolution is 360 degrees, and we have to work in radians for these 2 questions. Okay, so let me do the next one, and then I'll explain why radians and not degrees. Okay. And so let's see here. How long until the rod spins up to a speed of 30 revolutions per minute? Okay, it starts at rest. It's going to spin up to 30 revolutions per minute, and I want to know how long. Okay, so what do we have here? Well, it starts at rest. Okay, it starts at rest, means that its initial speed is 0. But what is speed when things are rotating? Okay, I mean, when you think of speed going down the street, you're thinking of like driving down a straight road. Okay, but this is the speed when you're going around in a circle. That's angular velocity. Okay, so the English is a little bit ambiguous, but when we say angular velocity, we mean the rotational velocity. How fast is the thing spinning? Well, it starts at rest, so the initial angular velocity is 0 radians per second. Okay, the after some time, it reaches an angular velocity of, or spins up to 30 revolutions per minute, like that. And that's not in radians per second. We need this in radians per second. So RPM is the way you'll see it written. Like, if you ever look at anything that's spinning, it's always written RPM like that. But think of it as revolutions per minute, okay, as that kind of a ratio like that. And the reason is that now we can convert, okay? So we have to convert away from the revolutions to radians, and so we'll use that equality there to form the following fraction: 2 radians divided by 1 revolution. Okay, that will eliminate the revolution. Okay, eliminate numerator here, denominator there, and give you 2 pi radians. And then the other one we have to switch over is minutes. 1 minute divided by 60 seconds. Okay, like that. All right, so what does that work out to? Let me do that quickly on my calculator. So it's 30 multiplied by 2 pi divided by 60, and malformed again. How come? There we go. It's weird. All right. Okay, and there it is, rads per second. Okay. Yeah, it turns out to be pi. That's actually the value of pi, okay, in decimal. And the reason is that you see you had 30, but 30 divided by 60 is a half. Half of 2 pi is pi. Okay, so that's why you got that number there. Anyhow, it starts at 0. It speeds up to 3.14 radians per second. We know that the angular acceleration is this number right here. All right, right there. All right, like that. And radians per second. And what do I want? I want to know how long. So that's t is equal to 0. Okay, and you say, well, what equation do I want to use there? And there's no theta information at all. Okay, and you go, all right, well, I'm trying to solve for t. I've got initial final omega and alpha, and you say to yourself, oh, this equation here. I guess this is the one we called equation number 2. Okay, plus that. All right, like that. Oh, whoops. Okay, and so okay, so now we're solving for oh, why did I put 0 there? How long? Question mark. Okay, so t is question mark, and so we're solving for t there, and this is pretty easy to solve. You just do it. I'll rearrange it symbolically first. So subtract omega naught from both sides, like this, and that's going to equal alpha times t. And then divide both sides by alpha, because we know alpha, like that. And that's going to equal t like that. And so t is going to equal all of this stuff here. Okay, so that was kind of trivial. I just switched around because we like thinking of the unknown as being on the left hand side. And so what's that going to give us? Well, we spin up to an omega of that. Its initial omega was 0, divided by an alpha of that. Okay, and that's going to equal fraction of a second, it looks like. Is it a tenth of a second? A little less. Okay, there we go, seconds. All right. Or I guess, rounding off, it'd be 0.080 seconds. Okay, because if we round off, to just three significant figures, this is a double round off. Okay, so there it goes. All right, so 0.08 seconds. All right, so how was that? Was that all right? Let me take a look here. All right, doesn't seem like there are any questions. Let's move on. Okay, so um, what's the tangential velocity? And then the centripetal acceleration. Okay, so the tangential velocity is vt, like that. I'll write it like that because I can't quite do subscripts. And what does that mean, tangential velocity? That means that, I guess if we could go back to that diagram just for a second here. Oh, geez. All right, hold on. There we go. Okay. So, well, that's getting a little bit messy. Let me just redraw it down here. No. Black. Okay. And here's the center. And now you have to kind of picture this thing spinning like that, say. And it's spinning like that. Okay. So it's spinning around at some speed. Okay. And I say here, what is the tangential velocity at either of the tips? Okay, because it depends where. So I'm actually want to know, like, imagine there's a red speck right there. Okay, I want to know how fast is this red speck moving. Now I know it's going along a circle, but it still has some velocity, some linear velocity, even though it's along a curve. Okay, so that is given by this formula right here, r times omega. Okay, and there's a series of three of these. They're all of the form linear quantity is equal to r times the equivalent angular quantity. So you see here, omega is the angular equivalent of the velocity, the linear velocity. Okay, and how are the two related? By r. This equation, or that sequence of equations, only works if this is measured in radians, or radians per second, or radians per second squared. The whole way that this is derived makes the assumption that you're working in radians. It does not work in degrees, it does not work in turns or revolutions or anything else, only in radians. And that's why at every point we're always converting to radians per second. You go, well, why can't I just work in, why can't I just work in revolutions per minute? And that's the answer. Okay, I mean, it would be kind of okay for these equations, it'd be okay for like these kinematic equations, but when you get to these kinematic equations, you'll get the wrong answer. Okay, so might as well just like switch to radians per second at the beginning. All right, so it's at the tip, and so let's go back to that diagram very quickly. You say, well, at the tip, tip measured from where? Like, how do I measure that r? And the answer is, it's measured. Let me do it in red. I guess it's measured from. Whoops. Measured from the axis of rotation to where it's acting. So that r is like that there. It's the same here, like when we had where the force was acting at 20 centimeters. Like all the r's in these problems, the radial distances, they're always measured from the axis. Okay, so you start at the axis, and then to wherever the point of interest is, or the point where the force is acting, that's how you measure r. And you say, well, how big is that r? Well, if the whole thing is 120, half of it is 60. So this r is going to be 0.6 meters. Okay. All right, so now back over here, you go, all right, well, r is 0.6 meters, and omega is 30 RPM, okay, and we converted that already. It was this number here, all right. And you say, well, what does that work out to? Well, I'll tell you in a sec. So it's basically pi times 0.6. It's this number right here. And if we work out the units, you see you have a meter there, and then you have over here a radian per second, and you go, that's weird. meter radian per second? How does that work? Because a velocity is just should be a meter per second. Well, remember what I said a minute ago, like radians are basically not a unit, and so you could just get rid of that radian, okay? And so it's just a meter per second. So there's the answer, okay, 1.88 meters per second, all right? So rounding off, it would be 0.88 meters per second. All right, good so far? All right, now there's two accelerations. There's the tangential acceleration. Maybe I'll EFG. Maybe I'll do what is the tangential acceleration? It's good to do so you don't confuse the two. Okay, so what is the centripetal acceleration? That's AC. That's calculated by R omega squared. Okay, so it's not actually part of that series that relates angular and linear quantities. This comes out of uniform circular motion, and I derived that earlier in the year. Okay, so here now we have 0.6, and we have the angular velocity right there, but this time it's squared. Okay, and that's going to give us a number like that's going to give us this number here. Okay, meters per second squared. And I guess rounding off, we could just write it like this. Okay. Oops. So that's a little bit more than half a G, right? Because a G is 9.8. And so half of that would be like 5. So this is a little bit more than half a G. Okay, so I mean, if something were on the end of this thing, it would feel like the centripetal acceleration is giving it half of its weight. Okay, and the tangential acceleration follows this pattern here. Only it's not tangential velocity, it's tangential acceleration, and it's not the angular velocity. What's the angular equivalent of acceleration? It's alpha, the angular acceleration. Okay, so I'll draw a picture of this in a minute, but like there's a centripetal acceleration, that's an acceleration to the center, and then there's an acceleration tangential, and the tangential acceleration is in the same direction as the tangential velocity. Okay, well, in this case it could be either in the same direction or opposite direction, okay, but not at some other angle. Okay, so what's this going to equal? It's going to be 0.6, like that. And alpha, what did we find alpha to be? We found alpha was that value there. Okay, and so this number is equal to this number here. Okay, and it would be again meters per second squared. All right, so there's the two accelerations, the centripetal and the tangential. And notice the two formulas. Centripetal is R omega squared, tangential is R alpha. Okay, and so now you go, well, what are these two accelerations? Like, how should I picture them? And well, go back to the diagram here. It's getting a little bit messy. Let me just create another one very quickly. So here's the bar. Here's the center. And here's our little red spot like that. The centripetal acceleration is towards the center. Let me do that in purple. I don't know why. Why not? Because I've got the colors, so might as well use them. So the centripetal acceleration. Centripetal means center seeking. Okay, the petal part is a Latin word that means seeking. Okay, petere. And so it seeks towards the center. And the other one, and I'll do that one in green, is the tangential, and it's this way. Okay, and it's AT. Okay, so they're like two components of the the acceleration. Okay, the actual acceleration. If you said, well, what acceleration would I actually experience? Well, you know what? These are like x and y components, and the actual acceleration. Let me do that in red. Would actually be this way, like that. But there's two contributions to this actual acceleration. Okay, there's a centripetal contribution. That's a contribution that comes because there's an acceleration towards the center. That's what keeps it on the circle. And then there's also an acceleration tangential, and that's because it's speeding up along the tangent. Okay, so there you go. Those are the two. Usually we don't combine them into one, but they are two different accelerations. In uniform circular motion, you have only the centripetal. You don't have the tangential. But when it's generalized rotational motion, you can have both. Okay. All right. So if there are no questions with that, we're done with that problem. Okay. And I'm just looking here. All right. So this next problem, I'm going to skip it. And the reason I'm going to skip it is because I realized after I wrote it, like there's only so many different variations you can make. We actually did something very similar to this. This was a ball rolling downhill. Okay. So we did one, I guess, the week just before the break. Okay. So I don't want to redo that because I want to practice something a little bit different. But if I were to draw a picture of this, let's go back to oh yeah, the whiteboard that keeps disappearing on me. All right. Let me just do it down here. It's basically, you have some hill like this. Okay. And you have a ball or a drum like this up here. And then it rolls downhill like that. And it's dropping some vertical distance h like this. Okay. And so the energy formula is mgh. It starts off with all potential energy. And it becomes all kinetic. But down here, there's two pieces of the kinetic. 1/2 mv squared plus 1/2 I omega squared. You know what this piece is because you've seen that before. That's the translational kinetic energy. You say, well, what's that? That's because it's spinning. Okay. It's rotating, and there is a relationship between how fast it's moving and how fast it is rotating, and that is the rolling without slipping formula, and it is V is equal to R omega, which should look familiar because that's like the VT over here. VT is equal to R omega. Okay. And they're slightly different. There's a slight difference in meaning between the two, but basically, you can relate the velocity and the rotation. This is for not slipping, no slipping. If it slips, well then all bets are off. Okay, but this is no slipping. All right. Eh, can't write on this surface. Okay, anyhow, there we go. Okay, I want to skip that because, like I said, we did that already. Okay. By the way, you say, well, what variations could you do on this? Well, it could go downhill. The other variation is I could have it going uphill. Okay, I could tell you how fast it's rolling and then go uphill. Okay, we didn't do that. But it's kind of trivial because it really doesn't matter whether it starts with kinetic energy, becomes all potential, or it starts with potential energy, becomes all kinetic. It's really the same formula. Okay, so slight variation. All right, I like I said, I want to skip that because we did do one like that before. Okay, I want to do this one. Okay, because this one's a little harder, and it's conservation of angular momentum. Okay, and so conservation of angular momentum, and it's even more than just conservation of angular momentum. It's conservation of angular momentum plus a mix with linear and angular momentum. So let me read it and I'll draw a picture because it is a little bit of a brain twister. So we have a disk, mass of 1 kilogram, radius of 5 centimeters, initially at rest. Okay, so you can picture this disk. It has a little 5-gram bullet plus some explosives on the edge. Okay, something like maybe a litge bit of TNT on the edge, or not gunpowder. I mean, not TNT. Okay. When the explosion goes off, the bullet flies off at 500 meters per second in a direction tangential to the edge of the disk. That might be the part that's a little bit hard to picture. Okay. And I should have probably said here, disk has a initially, which is free to rotate around the middle and is initially at rest. Okay, so sorry, I'm modifying the problem here, but basically you have this disk, it's free to rotate around the middle, and it's initially at rest. Okay, but I think we can picture that when the bullet goes flying off, because it's been fired off at the edge of this thing, then the disk is going to start rotating in the opposite direction. So I want to know how fast is the disk spinning after the bullet is fired. Okay, so you say, well, I can't picture that. So all right, let's switch to the whiteboard, and let me create another whiteboard here like this. Okay, and so this is what I'm picturing. So we have this this disk here, like, oh, that's terrible. All right, there we go. There's a disk. I don't know if that's any better, but whatever. There we go. There's a disk like that, and you know, it's sitting at rest. And at the very edge here, I have this like bullet here like this. And I don't know. Maybe there's like a flat little surface here like this. Okay, and then between the two like this, there is some explosive. Okay, so I know I didn't mention that little black wedge here, but you know, like that. But the reason is that, you know, when this thing explodes, what's going to happen? Well, the bullet is going to go this way, and I did say tangential at 500 meters per second. Okay. Well, what do you think is going to happen? When the bullet goes off that way, the disk is going to start spinning in the opposite direction. Because when the bullet gets fired, I know there's an explosive in there, but the bullet's got to push against something to get turning, okay, to get moving. And what it's pushing against is the disk, okay, via that little tab there, okay, and that's going to cause the disk to start spinning, okay. And you go, geez, how in the world would I ever do this problem? Okay, it looks a little difficult, but it's not that bad if you think about it in terms of angular momentum. Okay, so angular momentum, a conservation of angular momentum. Let me write the conservation law. L is equal to L primed. Okay, that's it. And you go, geez, that doesn't give me a lot of information. I know all it says is that, you know, whatever the angular momentum is before, it's the same angular momentum after. Okay, and so, well, what's the angular momentum before? Well, not only is the disk at rest, but I should have probably said, you know, the bullet, which is sitting there on the disk, it's also at rest. Everything is at rest before that explosion goes off, and so the angular momentum before is 0. Okay, and let's not worry about the units right now. Okay, so what's the angular momentum after? Well, the angular momentum after is going to be whatever the angular momentum is of the bullet plus the angular momentum of the disk. Okay, how do you spell this? There we go. Okay, so it's the angular momentum of the bullet and the angular momentum of the disk. Okay, and you say, well, how do I calculate, say, let's do the angular momentum of the disk first, because that's the easiest one. How do I calculate the angular momentum of the disk? Okay, so this is where the definition of angular momentum comes in. It's the moment of inertia of the disk multiplied by the angular velocity. Let me get an omega from up here. It's the angular velocity of the disk. Okay, and this is like after the explosion. Okay, I guess I could put a little prime there, but it's going to make a mess if I do. So it's just basically the moment of inertia of the disk multiplied by the angular velocity of the disk. You say, well, what's this angular velocity of the disk? That's what we mean here. How fast is it spinning? So we're actually solving for that. Okay. And so you say, well, what do I know here? Do I know the angular momentum of the disk? Well, no, but with the bullet and the angular momentum of the disk together, that should equal 0 because it's equal to 0 beforehand. Okay, so after we do this, then we get the bullet, and then we'll be able to solve for that. All right, so let's do one step at a time. What's the what's the moment of inertia of the disk? What's a disk? It's rotating around the center. If you look at the formulas for moment of inertia for a disk, it's mr squared, like that. Okay, so 0.5 multiplied by the mass, which is 1 kilogram, multiplied by you know what, I'm going to change this, not that it's a big deal, I'm going to change it to 50 centimeters radius. Okay, I don't want my number to be too big. Okay, that's all I did. Only reason I did that. So 50 centimeters is half a meter, like that, and we have to square that. Okay, so that r is 50 centimeters or 0.5 meters, and if we work this out, if I'd done 0.5, if I'd done 5 centimeters, it would have turned out to be tiny. So not that that's a problem. It just, I would rather not work with numbers that are too small. Okay, so there we go. There's the moment of inertia of the disk. Okay, and we don't know what that is. Okay, so now, great, we've done this one. What about this one? This is the hard one, or harder one to picture. You go, well, what's the formula for that? Well, it's going to be equal to, same thing, moment of inertia. Get rid of the space there. Moment of inertia, but not of the disk, but of the bullet. And not the angular velocity of the disk, but the angular velocity of the bullet. And you go, this is like totally weird. Like, what do you do with that? Because if you go back to the picture, there we go. If you go back to the picture, the bullet's moving in a straight line after, right? So, like this is after the explosion, it's moving in a straight line. And you go, if it's moving in a straight line, how does it have any kind of angular velocity? And also, how does it have any kind of moment of inertia? Well, don't think about the thing, the bullet when it's like way out here. Let me do this in purple. Don't think about it when it's out here. Okay, think about the bullet right there. So the explosion has occurred, but it's just leaving the disk. Okay, well at this point you might say, well, what's the moment of inertia of the bullet? Like that. And what is the bullet? It's just a point mass. And so you're going to use the formula mr squared. Right? Because that's the moment of inertia of a point mass. Okay, this is like the child jumping on the merry-go-round in my pre-recorded lectures. Okay, so I say, okay, great. Well, what's the mass of the bullet? And the mass of the bullet, what did I say it was? It was 5 grams. Okay, so that's small. All right, so the mass of the bullet is going to be 0.005 kilograms. All right. And then you say, okay, well, what is the radius? Well, how far is the bullet? Remember the radius in these problems, these r's, they're always measured from the point of interest to the axis. And you say, how far is that? And the answer was half a meter, 50 centimeters or 0.5 meters. Okay, there you go. So that gives you the I of the bullet, the moment of inertia of the bullet. You might go, well, what's the angular velocity of the bullet? And well, you remember the VT is equal to R omega? Well, just turn that around. Okay, so or just rearrange it. Omega is basically VT over R. So it's the velocity of the bullet divided by R. Okay, and what's the velocity of the bullet? I think it was 500 meters per second. And what was the radius? Well, the radius, I made it 0.5 meters, like that. And there you go. Now, the reason you picture the bullet here, like right out there, let me use a different color. I don't know, I'm running out of colors here. Green. Okay, the reason you picture the bullet here to do this calculation and not out here is because it gets weirder and weirder to calculate R. You see, like R, if the bullet's out here, then you got to do like an I like that. Okay, and then this one gets even weirder too. Okay, so basically there's no reason why you have to like calculate I and omega right here. Okay, you could do it there, you could do it there, you could do it there, but the thing is like how would you know the numbers there? How would you know R there? Okay, how would you know R there? But over here at that point where it's just leaving, that's where you do know it. Do know R, and so it's best to always just think what's I and omega when the thing is first leaving, or if the bullet is hitting it and getting embedded, it's just as it's getting embedded. Okay, so I hope that makes sense, but basically over here now, let me just redo that here. Now we know how to deal with that. The moment of inertia of the bullet here, that I bullet, that's going to be mr squared, where m is 0.005 kilograms, that's the 5 grams, and r is 0.5 meters, like that, squared. Okay, and that is a small number, but I'll work it out. Let me just do this on. It's this, and what's the other one? 0.5 multiplied by 0.5 squared, like that, and it's this value right here. Okay, kilogram meters squared, like that. Okay, and what about the angular velocity of the bullet? Well, that's just going to be v divided by r. Okay, went through that on the other whiteboard. And v is, how fast did I say it was traveling? 500 meters per second. It's 500 divided by 0.5. Okay, and what's that, 1,000, I think? Yeah, obviously. I don't know why I'm using my calculator. So obviously 1,000. Okay, and there you go. So there's the omega, and that would be in radians per second. Okay, and then finally, now we can put that all back and calculate the moment of inertia of the bullet, the moment of inertia. Sorry, not the moment of the angular momentum of the bullet. It's going to be I, this number here. You know what? I'll put the units in there so you can see what the units are. Okay, not that they're not very interesting units, but like that. And what's that going to equal? Well, just take this number and move the decimal over 3. So it's like, here's the decimal, 1, 2, 3. The decimal moves to there, and there you go. And the units are kilogram meter squared times, drop the radians, so radians per second, but drop the radians. There you go. They're kilogram meter squared per second. That's the units of angular momentum. Not very interesting units, but nonetheless, there it is. Okay, so you say, geez, I'm getting lost here. What are you doing? Well, we're doing the total angular momentum after. So let me just take that down here. Okay, total angular momentum after. And we now have that the total angular momentum after is 0, right? Because it's 0 before, nothing's turning before, so it has to be 0 after. Okay, and then you've got the angular momentum of the bullet, and we've got that now. There it is. Plus the angular momentum of the disk. Well, we don't have the full angular momentum of the disk. We've got the moment of inertia of the disk. Let me just write it like this. Whoops, that should be a plus. Right? So the total is 0. Angular momentum of the bullet is 1.15. Angular momentum of the disk, well, we don't have that. We have the moment of inertia of the disk, and we're trying to find that. Okay, so that's going to equal 0 is equal to 1.25 plus moment of inertia of the disk is this number right here. Oh, this turns out to be an interesting number. Okay, multiplied by omega of the disk, and ta-da! Well, we bring it to the other side. Just one more step. That is equal to that. So guess what you get? Get that omega of the disk is equal to negative 10 radians. Whoops. Radians per second. Okay. So the disk, and it's negative because it would be spinning in the opposite direction, okay, to the bullet, okay? So the disk would actually compensate by spinning in the opposite direction at 10 radians per second. All right, so a little bit involved, and this problem here, I didn't like walk you through it, okay? Like on the test, you say, geez, I'd be overwhelmed, if I were to up the standards of the course, I could just throw this at you, but usually I walk you through these problems. So, I'd have you calculate the moment of inertia of the disk. I'd have you calculate the moment of inertia of the bullet, the angular velocity of the bullet right after the explosion, and then have you put them all together to get the final answer. Okay, so I wanted to do an angular momentum one. So is that good, everyone? I think the class is probably more than done. So there we go. How's that? Okay. If there are any questions, if there are no questions, we can just end the stream at this point. I'll just wait a second. Oh, I got to get the next class ready. Yeah, this one was a longer class, but okay. So let me just ask in the chat here: is everyone okay? All right, got a lot of thank you. Well, thank you guys. All right, so all right, well then, let me just say goodbye. Bye bye.